Hey everyone, Mr. Hauk here. In today's video, we're going to be exploring the parent functions for sine and cosine. Let's go ahead and get started. What we're going to do is we're going to first look at a discovery activity. And in this discovery activity, notice that you're given a chart, and the instructions are to use the unit circle to fill in the chart. So we are given the angle in degrees, and we want to find the radians that match that angle in degrees, the cosine of that angle, and the sine value of that angle, all the way from 0 to 360 degrees. Then notice that we want to take this table that we create, and we want to go ahead and graph y equals sine of theta and y equals cosine of theta. So that means that for y equals sine of theta, we're going to use the angle as the x value, and we're going to use sine of theta as the y value. Then when we go to graph y equals cosine of theta, again, we're going to use the angle as the x value, and we're going to use cosine of theta as the y value. Go ahead and take a couple of minutes, use your unit circle to fill in that chart, and try to sketch the graphs of those two functions. Okay, here's what I'm getting. So here in blue, notice that I have my angle converted to radians from degrees, my cosine values are in green, and my sine values are in red. Let's go ahead and take this table and let's try to graph y equals sine of theta and y equals cosine of theta. So we're starting here with y equals sine of theta. I'm going to go ahead and label my y-axis. I'm going to label this up here as 1. This right here is -1. Same thing for y equals cosine of theta. So notice that for our graph here, the main x values that we're going to be looking at are 0, pi over 2, pi, 3 pi over 2, and 2 pi. So let's go ahead and fill in our chart accordingly. So first we're going to look for an x value of 0. So again, keep in mind that the angle will be x, and for this graph the sine value will be y. So when the x value is 0, the y value is also 0. So let's go ahead and plot 0, 0. Next up, we're going to look at the x value of pi over 2. Well, when x is pi over 2, y is equal to 1. Then we want to look for the x value of pi. So when x is pi, the y value is 0. Next, we're looking at an x value of 3 pi over 2. So when x is 3 pi over 2, the y value is -1. And then last, we're going to look for an x value of 2 pi. So when x is 2 pi, notice that the y value is 0. Now, you could have tried to plot all the points in between, and it would have been perfectly fine. But we can see exactly what's going to happen here. So let's go ahead and trace the graph. Okay, this is the image that we're getting for y equals sine of theta, or at least this is the sketch of the graph. Now let's do the same thing for y equals cosine of theta, but notice that this time we're still going to let theta be the x value. Okay, still let theta be the x, but now the y value is going to be the cosine of theta. Okay, so we're going to do the same thing. First, we're going to look at an x value of 0. So when x is 0, now the y value is 1. So let's put a point there at 0, 1. Next, when the x value is pi over 2, we get that the y value is 0. So let's put a point at pi over 2, comma 0. When the x value is pi, the y value is -1. So pi -1. When the x value now is 3 pi over 2, the y value is 0, so 3 pi over 2, comma 0. And then lastly, we want to look for an x value of 2 pi. So when x is 2 pi, y is 1. And let's go ahead and try to trace this graph as well. Looks kind of shaky, but that's the image that we're going for here. So we call this y equals sine of theta and y equals cosine of theta. These are the parent functions for sine and cosine. Now what we want to do now is go ahead and compare our sketches with what the actual parent functions look like using Desmos. If you're using, if you have your phone and you have a QR code scanner, you can go ahead and scan that QR code to pull up a Desmos calculator. I'm going to go ahead and pull up Desmos to run side by side here. All right. So let's go see what happens here. Let's make sure we're set to radians. We are. And One thing that I learned from another teacher, Mr. Moskowitz, over at Mountain View, is that we can actually set our Desmos graphs to run in intervals in radian intervals. So if we look at the x-axis and we set our step to be pi over 4 or something like that, then when we go to graph, notice that our x-axis, instead of being from like 1, 2, 3, so on and so forth, we can set our x-axis to go in steps of pi over 4 or pi over 3, pi over 2, whatever we need. Okay? Let's start by graphing y equals the sine of x. And notice the image that we're getting here, I'll go like that. The image that we're getting here, pretty much identical to the image that we graphed, that we sketched from our table. So notice that we have the point 0, 0, we have the point pi over 2 comma 1, we have the point pi 0, 3 pi over 2 negative 1, and 2 pi 0. Okay, pretty cool. Now let's try y equals cosine of x. And I'm going to hide sine of x for the time being. Again, just like our graph here, notice that we have the point 0, 1, pi over 2, 0, pi negative 1, 3 pi over 2, 0, and 2 pi comma 1. So our graphs that we derived from this table here are accurate according to Desmos. So let's confirm a couple of facts that we already knew that we can also see from the graphs here of y equals sine of x and y equals cosine of x. Notice that for both, the domain is the set of all real numbers, and if I pull up my graph of Desmos, I can just keep going on and on to the left and to the right. We have a function, or these two functions just continue to move in this pattern infinitely to the left and right, which means they have a domain of all real numbers. Okay, so that's one fact that we can see from our graph. The range for both of these functions is also -1 to +1. So if we look at our graph here in Desmos again, we can see that the y values, and I'll use these right here. Let's hide that one. Hide that one, all right. So we can see that the y values never grow larger than +1 and never grow smaller than -1, and they're going to oscillate back and forth about the x-axis. So our range is tracked in between -1 and +1, and that's going to be inclusive, -1 and +1 being points that are included in the range. The other thing that we can see, and we will look at these functions individually for this, if we look at our sine function, we talked about odd symmetry, and a function has odd symmetry if you have symmetry with respect to the origin. And if we look at the sine function here, I'm going to make Desmos a little clearer here. If we look at the sine function, every point, for example, if we look at pi over 2 comma 1 and negative pi over 2 negative 1, they are reflections of each other across the origin 0, 0. So the y equals sine of x has origin symmetry. But if we look at y equals cosine of x, notice that the symmetry is with respect now to the y-axis. If I take the point pi negative 1 and I reflect that across the x-axis, I'm going to get the point negative pi negative 1. So again, the sine function is odd because it has origin symmetry, and the cosine parent function is even because we have y-axis symmetry. So a couple of questions I want us to think about here. Number one, how many x-intercepts do the parent functions of sine and cosine have? Well, keep in mind that an x-intercept is a point where a function crosses through the x-axis. And if we look at our graphs that we just generated in Desmos, we'll notice that because of the fact that the parent functions of sine and cosine are repeating endlessly, infinitely, all the way to the left and all the way to the right, it's going to cross through the x-axis an infinite number of times. So for both cosine theta and sine theta, let's go ahead and write this down. So for both parent functions, they have an infinite number of x-intercepts. So how many x-intercepts do the parent functions of sine and cosine have? An infinite number. of x-intercepts. Because again, both functions are passing through the x-axis an infinite number of times, forever to the right and forever to the left on the x-axis. Well, if we have an infinite number of x-intercepts, what about the y-intercepts? Well, again, if we look at our parent functions here and we look on Desmos, well, we can see that for the cosine of theta, the y-intercept is at 0, 1, and for the sine of theta, or the sine of x, the y-intercept is at 0, 0. And notice that since a y-intercept is the place where a function passes through the y-axis, each cosine and sine only have one y-intercept each. So we'll say one y-intercept each. And to be specific, it is 0, 0 for y equals sine of x, or y equals sine of theta, and it is 0, 1 for y equals cosine of x, or cosine of theta. All right, and then last we want to think about how might the graphs of sine and cosine be related? Well, if we look at our graph in Desmos especially to explore this question, notice that they're pretty much identical, except that, if we take a look at sine first, it seems that sine is the same graph as cosine, just shifted a little bit to the right or left. You could say the same about cosine. Cosine looks like the sine function, just shifted to the right or left. So there's definitely something going on here with sine and cosine, and they're obviously very closely related to each other. We're actually going to derive the relationship in an upcoming video. Okay, so this is Mr. Haug for parent functions of sine and cosine.